Welcome to April 16th LeetCode Challenge. Convert binary search tree to greater tree. Given the root of a binary search tree, convert it to a greater tree such that every key of the original binary search tree is changed to the original key plus the sum of all the keys greater than the original key in the binary search tree. As a reminder, a binary search tree is a tree that satisfies these constraints. So you have the left subtree of a node contains only the nodes, the keys less than the node's key. The right subtree of the nodes contains nodes with a key greater than the node's key. And both the left and right subtrees must also be in the binary, must also be a binary search tree itself. So we're getting to example number 1 here. It's binary search tree, and we see that the 30 is the value, which is basically we want to convert it to a greater tree. So we have the binary search tree being 4, 1, 6, 0, 2, 5, 7, null, 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 3, null, 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 8. And to convert that, we need to make it to a greater tree. So basically, find all the sums of the tree and then put it in the order that it's binary, such that its values fall from the 30 to 36 to 21, 36, 35 to 26, 15, 33, and 8. So basically that means that we want to basically find the sum of the values put together. So for example, so 8 plus 7 is 15, plus 6 is 21, plus 5 is 26, plus 4 is 30, and then you want plus 3 is 33, plus 2 is 35, plus 1, 36, and then plus 0 is 36. So that's kind of how a greater tree works. And we have the value of 0 null is 1. Then the sum of all the greater tree is 1. So constraints are that the number of nodes in the tree is ranged between 0 to 10 to the 4. The value of each node is between negative 10 to the 4 to 10 to the 4. All the values of the tree are unique, which is good, and it's guaranteed that the root is a guarantee to be a valid binary search tree. All right. So to solve this, I think I'm going to go with the simple route of using recursion. So to provide a reverse in-order traversal via recursion, we're going to use a call stack to return the previous node, so we can easily switch to the node in reverse order. So to apply this algorithm, what we want to do is essentially ensure that the current node exists, and then ensure the current node exists. So if root is not none, what we want to do is basically perform ensure that the current node exists, recurse on the right subtree, visit the current node by updating its value and the total sum. So we could do that by convert binary search tree. We call that on the right subtree. And then next thing you want to do is visit the current node by updating its value and the total sum. So we also want to update the sum, which is the total sum, being incremented by self.total, and then root.val, and then we want root.val to be assigned to self.total, and then finally we recurse on the left subtree as well. Self.convert binary search tree on root.left. So if you know that recursing is going on at root.right, it properly updates the right subtree, and then recursing on root.left properly updates the left subtree. We're guaranteed to update all the nodes with a larger value before the current node. All nodes are smaller value afterwards. So once that's the case, we exit the loop, and then we essentially return the root. So we're changing everything in place. Let's run this. let's see, self dot, whoops, I need to initialize I'm going to use this class actually. Self. All right. Let's run this. Alright, yeah, I just had to make this init function there. Alright, so time complexity wise, they go of n, because the binary search tree has no cycle in it by definition, so that the convert binary search tree gets called at each node no more than once. Other than that, the recursive calls binary search tree does a constant amount of work, so it's linear, so it calls it in a linear runtime. Space complexity is also big of n as well. Prior, we know that the convert binary search tree function is linear, calls it linear time, so we can always use the entire algorithm as linear space complexity, because we know at worst case the tree only goes to right or only left subtrees, and then we call on the stack until it grows to the n longest path reach, which includes all n nodes. Alright, that's it. Have a great day.